Hello, everyone. Thank you very much for joining us today. Welcome to our TAP testing panel discussion. My name is Cristina Sesma from Productive Machines. We use the results of a TAP test as an input to our technology to avoid vibrations and optimize feeds and speeds. And what we have realized is that there are a lot of misconceptions about TAP testing. So people may think, it takes too long or it's too difficult or things like that. So what we would like to do now is get a feel from the audience as to what your perception is and find out how long do you think it takes to perform a TAP test for one tool. So if we're going to run a poll now, so if you could submit your answers. So we're seeing a lot of people think it's very quick, actually. Maybe we have a bit of a biased audience here. I think people are still sending answers. Okay, I think everybody's finished now. We're going to share the results. So about 62% thought it was 10 minutes. Fantastic. And 38% thought it was an hour. Another thought it was 1 day. Okay, very good. Excellent start. So the reason why we're here basically is we've invited this panel of experts to try to demystify TAP testing so they can share the knowledge and their experience and throw a little bit of light into this art. And there will be the opportunity to ask questions to the panel at the end. So you could use the Q&A section. So please feel free to type your questions during the panel as you think of something, and they'll take the questions at the end. And now, without further ado, let me introduce our amazing panelists. We have Kareema Hilton from the National Manufacturing Institute of Scotland, NMIS. We have Dr. Peace Onawimi from the Advanced Manufacturing Research Centre, the MRC, our neighbours here in Sheffield, and Glenn Rutherford from the Advanced Manufacturing Innovation Centre, MIMechE, in Northern Ireland. So would you like to tell us a little bit about your research centres and, where you work and what's your role there? So if I can start with you, Kareema, What you want to tell us, please?
Okay, well, thank you very much, Christina. So I am Kareema Hilton. I work for the National Manufacturing Institute of Scotland, as Christina said. You can just call it NMIS for short, because it's a bit of a mouthful. So we are the only Scottish catapult centre in the UK. We have a host of capabilities, but just to summarise them for you, there are 5 centres within NMIS. We have the original one that everyone probably is aware of, the Advanced Forming Research Centre. We've got the Lightweight Manufacturing Centre. We've got the Digital Process Manufacturing Centre, the Manufacturing Skills Academy, and the centre that I belong to is the Digital Factory. So within the Digital Factory, we have CNC machine tools, additive capabilities, digital processes, robotic, and a lot of augmented reality and all those types of processes in itself. So we do have a host of capabilities within our centre. That's us.
Thank you very much. Pete, would you like to tell us a little bit about the MRC?
Yes, it's the Advanced Manufacturing Research Centre, University of Sheffield. And yes, as Kareema said, also we have a lot of capabilities from the aerospace to automotive and so on. We have different branches of the AMRC, one at Sheffield, one in Preston, one in Wales. And yeah, so our work is to research, develop, we work with different businesses as well as industries to be able to improve process. We make prototypes, we improve the manufacturing processes and everything in order to make their work effective. So we do a lot of things in improving processes in manufacturing centers. So that's what we basically do. So make things better from software up to physical work on the machine. Yeah.
Mm-hmm. And your role?
My role, I'm the technical lead in the dynamics team for the subtractive technology.
Thank you very much. And how about you, Glenn?
Hi, afternoon, everyone. Yeah, Glenn Rutherford. I'm the team leader in MIMechE, Advanced Manufacturing Innovation Center. I'm getting used to the rebranding. We were formerly NITC. So yeah, we were a smaller, I suppose we're aspiring to be a catapult. We're a smaller center based in Northern Ireland, but we have a good range of capabilities as well, like the other centers. Areas of design, digital engineering. We have a polymers and composites research center as well. And as I mentioned, I'm team leader for machining and metrology. So anything manufacturing related and automation related, we cover those areas as well.
Thank you very much. So we're gonna run another poll to just find out whether tap testing is a common practice in your place of work, even if you're not necessarily doing it yourself. So we're gonna launch in the second poll now. It's just a yes or no answer. Okay. So so we have a 66% common practice and 34 no. Okay, so that is it is, like I say, I think we have a bit of a biased audience, but this is really good because then for that 34% that perhaps are not as familiar with it, they can find out a lot of things today. So I'm going to ask the panelists, in their opinion, how long do you think it takes to perform a tap test for one tool? So Glenn, what's your opinion on this?
Yeah, I would have answered 1 hour. Let me qualify that. I mean, it's quite quick for one tool. Getting the data is a matter of minutes, but go down, set up the laptop, mount your accelerometer, and maybe if you want to, ultimately you need to analyze the data and maybe do a test cut to validate the results. So it can be short or it depends on how much you're doing, but I would estimate an hour to do the supporting tasks as well. Okay,
so the actual tap test is quite quick, but then obviously the analyzing and everything else. I think one thing to note is that obviously this can be done outside production time offline, I guess.
Well, if you're tap testing a machine tool for trying to optimize speeds and feeds, you will be tap testing your tool assembly within the tool, within the machine spindle. So it can be disruptive to production, but obviously you try to minimize that, choosing when you
that's what I meant, that you can choose your times to do that. Yeah. Okay, Kareema, what do you think according to your experience?
Yeah, it depends. Also access issues as well, but I would say about half an hour to an hour to tap test. But I completely agree with Glenn. If you're thinking about analyzing the data, now this can be done once the tap tests have been completed, so you can then put the machines back in production. But it can take quite a while to analyze the data and make sure that you're optimizing it properly. But yeah, half an hour to an hour, especially with the new technology we have nowadays, it's a lot quicker than it used to be when I first started.
Very good. How are you, Peace?
This is only based on the fact that tap testing is is something I do all the time. But 10 minutes is what will take me. But yes, as the others have said, to analyze the data, if you're just going to look at the FRF and that's it, then 10 minutes done for me. But if we're going to analyze it, then it could take a couple of times to do that. But for tap testing itself, it's very quick and easy to do.
Excellent. Okay, so do you want to just tell us, please, a little bit more about, for the benefit of the people that perhaps a little bit less familiar, what is actually tap testing? What results do you get? How do you do it?
I've been trying to look for the best way to go about saying what tap testing is without having to go into too much words and big words. So basically, I'm going to say it's a system we use to understand the dynamic and the dynamic characteristic of a structure. So a structure can be your machine tool, It can be your part that you're machining. It can be anything, basically. But this is just to see how flexible your machine tool assembly is to get the FRF of the tool. And what is FRF? That's the frequency response function. This describes the vibration response of the force input by the frequency domain. So what am I looking for? What I'm looking for in a machine tool is, what is the trigger? What is the natural frequency of that structure? So each and every one, it's like the fingerprint, isn't it? Each and every one have a trigger. So our machine tools or our parts to have a trigger during machining processes. So what natural frequencies do I want to avoid? To avoid chatter, to avoid noise and everything during the machining processes. So it enables us to identify the natural frequency. What is the stiffness of your structure? What is the modal mass, as well as the damping of each vibration mode? Please note that each structure is different, and it's going to have different natural frequency. In some cases, just one. Other cases, it might be 5 or more. So it depends on what structure you are tap testing. And how do we tap test? All we need is an hammer, an accelerometer, or in other cases, a non-contact measuring system, such as laser sensors, capacitive sensors, and all that. And all we do is strike with the hammer, collect the data with the accelerometer from the other side. So on the opposite or perpendicular in some cases, and you use the data acquisition center system to acquire your data to measure the FRF. And this can be used for as we have said, for the analysis in the processes and to optimize your process. So basically, that's all tap testing in one go.
Very well, thank you very much for that. And Glenn, on to you. If you can tell us who uses tap testing and when, give us some examples of industries and applications that you've experienced.
Yeah, I suppose primarily, well, it's used in industry, used in manufacturing companies involved in machining metal. It can be applied to soft and hard metals. It tends to work. So hard metals can be a bit more challenging because of damping effects, but largely, if you're machining components, whether it's automotive or aerospace or other sectors, and you want to improve your machining efficiency, possibly increase your speed rates and your feed rates, your metal removal rates, tap testing is very good. So more and more, I think, well, in Northern Ireland here, we've quite a few advanced manufacturing companies, and they would use these services. Quite often they would contract them in as a service from a technical center, people like us represented in the panel. But in recent discussions, some of those companies who have seen the benefits of getting a stable process, getting a more efficient process, are talking to us about buying equipment and training and some of their own people to do the test. So I suppose, yeah, you can either contract in the services if you're not doing it very much, or develop your own capability. And I think the tools, Kareema mentioned the tools are getting more user-friendly and easier to use. So the people who would use it within a typical organization, a manufacturing organization, it would tend to be your manufacturing engineers, your CNC programmers who are responsible for engineering the process. So if it's a machining process and they're writing programs, they're good guys to have this toolkit in their pocket to be able to optimize the process that they're responsible for.
And would you say, do you think of a typical industry, or does that apply to anybody? Yeah,
thanks. Well, my background's aerospace largely, and some of the companies we work with would be in the aerospace sector. Certainly they would be using it for aluminium machinings, titanium parts as well. And so my experience has been more aligned to aerospace, but it's not limited to that. It can be anybody, it could be automotive, it could be other sectors as well.
Very well, thank you. Kareema, perhaps you can tell us a little bit about the benefits for the user. Why tap test?
Yeah, so there's we touched on it slightly. So there's two types of components that we can tap test. Peace had mentioned that you can tap test the cutting tool, but you can also tap test the part itself. So in terms of tap testing the cutting tool, in industry, you can find that the challenges they face are the experience chatter in industry. Maybe a machine tool operator will run a tool path and they'll hear chatter. And often in industry, what an operator will do will turn the feed rate down. That is not necessarily the most optimal and the best situation or the best solution to that. So this is where we're putting science behind the method and the feeds and speeds selection. So what we can do is, instead of telling someone to turn the feed rate down, we can tap test a cutting tool. We can look at a stability lobe, which is the depth of cut, a graph that's got the depth of cut versus the spindle speed. And actually it'll give you a graph and you will get a sort of sweet spot. So sometimes the sweet spot is not always slowing the cutting parameters down. It can actually be to speed up the cutting parameters. And this is what the tap test technology can support with. So then when you optimize the feeds and speeds on your cutting tool, you can actually speed up the process rather than slowing it down, and you can increase your productivity. So this is a way that as a massive benefit for using the tap test kit to help to select cutting parameters. You might find in industry as well that you speak to your tooling suppliers, they'll give you their feeds and speeds, which they probably calculated in experimental conditions. So they don't have the same cutting tools that you've got. They've not got this, the same cutting tool, but they don't have got the same CNC machine tool that you have. So cutting using your own CNC machine tool can be different to the way they've done it. So using the tap testing capability can help to select optimal cutting parameters. There's also a benefit of using tap testing capabilities to get the dynamic stability of a part itself. So you might find that you tap test a cutting tool and you tap test a part, and actually the part is more flexible than the tool. And in that time, in that sense, you don't really need to change anything with the feeds and speeds. What you want to do is try and make your part more damped or more stable. And to do that, you'll have to think about redesigning the workpiece. So there's really good insight you can get from tap testing and to understand more about your whole system. And this is a way that, like we are, all RT was here, this is the way that we can put science behind what people probably have done in the past. So I do know in industry, people have had a part and they thought this part is not really got the best setup, and they just get a big metal rod and hit the part with a rod, and you can hear that it's not very well damped. So this is our way of putting science behind what people are actually doing, but we can validate as well what they're doing. And now we can do it in 10 minutes, like Pisa said, really quickly, and try to support companies and industry as well.
Oh, that's really good. And also that's prior to manufacturing, right? So you're reducing waste, and presumably by avoiding the chatter, you're also extending the tool life.
Absolutely, yep.
Yeah.
And also we can use it to improve productivity in a situation where you don't want trial and error. That's the best way to go.
Yeah.
And that way you avoid waste and all.
I don't know if Glenn, do you want to add anything else into the benefits? What's in it for the user?
Yeah, I mean, good points have been made there. I think, yeah, getting you're engineering a better process up front by doing this task. Essentially, you're adding a little bit of time onto what you would do normally, but once you've got those parameters, speeds and feeds locked in, you've got a stable process, and you're getting those benefits mentioned of better tool wear, better productivity. You're getting that time and time again as you're in production making parts. So a little bit of investment up front more than pays back in the long term.
Very good. Okay, so let's have a look at the audience to see if we've got any questions coming through. So I go here. From the explanation that Peace has given, it sounds like this test might be a bit difficult to do. Is that correct? How does the difficulty justify the benefits?
No, it's not difficult to do. It's actually very, very simple. And a good example is when we went to the future metrology lab, productive machine had this tap test competition. And people actually who have never tap tested were able to do it within seconds. So it's not difficult to use. It's actually very easy to use. And the equipment are actually very, 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 very easy and quick to use. The armors are very light. And when you're tap testing, you're just eating very lightly, like you're touching. So it's not difficult, but there are a lot of benefits with it. So that's why I said 10 minutes, I'm done. So
Yep.
I think it's
Yeah.
worth saying too. I mean, Peace, you're doing this day and daily very often. You know, I think with anything new, you know, there's a fear factor, a fear of the unknown. So
yes.
I would encourage you, you know, to get alongside somebody that's using the equipment and understand it, because it does take, you know, if it's not something routinely used in your workshop, it's new, it's different, and you're unsure, and that's perfectly natural. So yeah, get alongside somebody that's done it before, and that's like many aspects of life, it's a good way of learning.
Yeah.
I think it is
Yeah.
part. Sorry, go on.
I was just going to say, I don't use it as much as Peace does, but I have been like probably every 6 months or so, and it does take a wee while to remember what you're doing, but actually that's why I've put down half an hour for me and not 10 minutes like Peace has said for herself. But the technology, like I've said, is so much better now. I remember back like 15 years ago when I used to tap test, and there was a lot of hit the police twice, please hit again, this is not working. And it was all a lot to do with the connections that were going through the data acquisition kit and things like this. And everything's a lot better now. So it is a lot more straightforward.
Mm-hmm. Got a few more questions coming in. So if the process is sped up, I think that would be for what you were saying earlier, Kareema, wouldn't that hurt the tool life? Can tap testing accommodate for that?
So yeah, when we speed up the actual feeds and speeds, it is all related to the vibrations of the cutting tool in the system. So the way that it works is you're sort of eliminating a vibration that will be not very beneficial for the cutting tool. So you're not actually hurting the tool as much. You're actually it's better for the tool, depending on what kind of feeds and speeds you do select. But Peace, you could probably enlighten everyone a bit more on that, but that's my understanding of it anyway.
Yeah, we've had a situation where we had a partner company, they were doing some tests, and the tool was snapping, for example, it was snapping. With the use of tap testing, we helped to improve the parameters, and it was not wearing as much and cutting more. So the use of tap test helps your tool because you're getting the right parameters. So you're going to avoid chatter. You're going to avoid those regenerative vibrations that keep going and destroying your tool. So it helps keep your tool safe as well as your spindle. Remember, this also will affect your spindle and your machine tool, and you're trying to protect those as well. So it has a lot of benefits. Yeah.
Another question. Does the stability loop change with changing tool engagement?
So I'm trying to remember doing the stability loop because it was about 6 months ago that I did it. I think whenever you do the stability loop, I can't remember putting the tool engagement in it, but the graph actually tells you the depth of cut. So that's not the tool, the radial depth of cut, but the actual depth of cut. And it can tell if you decide you want to change the axial depth of cut to like 2 to 5 millimeters. It'll tell you the best spindle speed to use, but I'm trying to remember if it does change with the axial, with the radial depth of cut. I don't know if Piece of you.
The stability loop now has the radial side of things. So you actually can pick up the radial as well as the exact depth of cut now. So there are more capabilities to it than in the past, yeah. So you can choose both with the spindle speed now.
And just to add to that, the more engagement you have of the tool, the forces are going to go up, and
Yeah.
we can do some experiments with Kistler. You can measure the forces, but the forces will go up, but also the stability can sometimes increase as well, because more tool engagement, more support of the body of the tool around the material. So yeah, it does change with tool engagement.
Mhm. Thank you very much. And what's the experience in spindle life from running spindles in resonance? Does it vary from materials, aluminium, grey cast, Inconel?
Yeah, so sorry, PC, you can go.
No, you go ahead.
Within the software, you specify which material you're cutting. So Glenn touched onto this. When the software has the force characteristics of the material, so you have to actually understand the different material itself. So they will have an effect on the stability loops itself.
And how can we apply this to turning? Is it possible to combine dynamics of workpiece and tool together?
Oh, yes, you can do that. So some softwares have capabilities. I know some software that have capabilities of the workpiece as well as the tool. As Kareema said initially, that in some cases your workpiece is very flexible than that of your tool. At that point, you consider your tool to be more rigid and you take the stability for that of the workpiece instead.
Mhm. Thank you. What about installation time and accuracy, especially for small tools if we use accelerometers?
So the hammers, yeah. We have different sizes of hammers depending on your structure. So we have a situation where we have tools that are very small, like 4mm tools. At that point, you need a very tiny hammer. It's basically this long, I think, if I can remember. Yeah. It needs someone that is well efficient. That you need to be more patient to take the tap testing. However, different hammer sizes for different sections. There's even a hammer that's that of a sledgehammer, which you can use for bigger structures. So yeah. So
Yes.
depending on your tool, depends on the accelerometer size and the hammer size.
It's funny you mentioned that piece because I'm looking into doing some dynamic stability on wind turbine sized parts as well. So it's the complete opposite. But again, like you say, as long as you get the right sensitivity and put it into your software correctly, you should get a very accurate
results. Yeah.
result.
Yeah, sensitivity is very important. You want to make sure the sensitivity of the hammer and the accelerometer is right when you're tap testing.
Mm-hmm. Perfect. And someone's asking, I assume tap testing works for milling and turning?
Yes, please.
The
It
answer
works
is
for
yes.
milling, turning, drilling, broaching, and so much more.
Yeah. And does the results of tap testing depend significantly on the tool flute length?
Yes. As your tool length changes, the dynamics of your structure changes. So for example, if I have a little shorter tool length, I expect it to be more rigid than when it's longer. So because it becomes more flexible. So yeah, it changes with tool length.
Okay, thank you very much. So this is all the questions from the audience. And now this takes us to the end of our panel discussion. We hope you found this really informative and that has cleared any questions that you may have as sparks an interest for anyone to explore tap testing. All the research centers here offer tap testing services and demos.
We have another question.
Oh, yep. Sorry. Yes. Yeah, a couple more
Questions
questions
keep
have
coming.
come through.
That's good. Good to see the questions coming.
Yes, that's always the best. Can any of you walk us through the process of tap testing for turning operation with a long 7-inch cylinder and a 1 inch diameter, and how it will help us improve our process?
My experience has been more with milling, so I'll pass that to some of my colleagues that have applied it to turning applications.
Yeah, I'm more milling as well, unfortunately, but piece you
Okay,
did.
so I'm the only one going to answer this now. Okay. So a 7-inch, that's how much in millimeters? That's around 100 and something, right?
175 millimeters.
Okay, that's a very big turning tool or a turning operation. Is the workpiece that's diameter or the tool itself? Who was asking this question?
Workpiece.
The workpiece.
Ah, okay then. So for that, knowing fully well that it's a very slender tool, I'll put the accelerometer in the x-axis and tap test on the other side from the x-axis of your two machines. So always remember that whatever axis you're taking, it aligns with your tool, with your machine tool. So tap test it from the x-axis, from the y opposite. So your accelerometer here, x on the other side, tap from the other side, then do exactly in the y opposite and in the z. And for that, you tap test your tool if you need to tap test your tool in the X, Y. Z is usually considered rigid because it's always engaging with your workpiece. As a result, it's always going to be more rigid in that area, but it depends on where your Z is in this situation, because some machine tools, it's different. So wherever it's engaging more with, but if you can tap test it, fine, tap test it. Then you go to your software. So we have different softwares available. I'm not going to try and showcase anyone at this point. And you put the FRF you've obtained for your tool into the stability loop, for the stability loop creation and the workpiece. Then you run it and you put your parameters. It is going to ask you what speed, that the maximum speed, for example, you want it. In some situation, you have a machine tools where 500 for turning, 500 RPM is the limit. So put it there and yeah, I run the simulation. Simulation is very quick. I think it doesn't even take up to a minute to run the stability loop simulation when you've input everything that needs to be done. Yeah.
Yeah, so the next question, PC, you've actually answered it, but to add to that, obviously put the cutting tool parameters in the software to get the optimal feed rates. But you could also use a microphone. So when you put the microphone to the part, you can hear chatter, and then that will be able to detect the frequencies that the tool is vibrating at when it's cutting. And then you can put it into another type of software, which can give you optimal feed rates as well that comes out of that. So that's from listening to the chatter. But the one that piece had mentioned there is from the stability loops, which goes through the software. So there's a couple of options there.
Yeah.
Excellent. Oh, one more. What is the duration we can see the impact of the technology if we have this capability tomorrow?
Immediately, actually. So you tap test, it's as we've mentioned, giving someone that's new to tap testing, I give you for setting up and all, taking your time, making sure everything is fine, analyzing, just yeah, roughly a couple of hours, and you find that when you've gotten that, you start doing it. In some situation and some organization, it's even used for their the whole of their tool part for manufacturing to improve it.
Very good. Thank you very much. So thank you very much for seems like we have got and answer all the questions now. And as I was saying, all the research centers here offer tap testing services and demos. Productive machines here, we have got a tap starter bundle that get you started, but also we have put together a page with information and videos, a tap testing hub. So if you go to our website, productivemachines.co.uk, oh, a couple more questions are coming. Okay, so to Kareema's point, am I clear to understand that vibration data can be used to verify chatter, and this
Yes.
data can be used in tap testing software?
Correct. Yep. It can.
Yes.
And then it's good because then you can then change the speed rate, so the feeds and speeds can be changed. You then put the microphone onto it again, and then hopefully you will find that there's no chatter as well. So that will verify that the chatter has been cleared. as well.
So the audio, what Kareema is saying, that the audio will tell you the natural frequencies that you are exciting at that point. So when you run it through it gives you the FFT, and you'll be able to know those frequencies, which are the natural frequencies. And then you know that this is what we're having trouble.
I think it's maybe worth saying as well, in terms of process stability, depending on how many flutes you have in your tool, whether it's 3 flutes or 4 flutes, you will pick up your tooth passing frequency. So as each tooth hits into the material, you'll get a reading on your FRF. So you'll see that you want that to be the dominant spec. If that's the dominant resonance, then you have a stable process. However, if you've chatter or vibration, there'll be other things more dominant than your tooth passing frequency.
Yes, and they're very visual. You see them, you can miss it.
And someone is asking if you can give us an idea about the benefits, the percentage of improvement in productivity.
It's a really complex question. Actually, it's a very good one as well. It's all dependent on your whole system. It can be quite a minimal improvement to a proper maximal improvement. It depends on what cutting parameters you are using currently. If you're using the machine tool suppliers feeds and speeds, it might be like a 5%, 10% improvement. If you're being very conservative and we think actually you could be running a lot higher, it could be a lot more, but it really depends on the whole system itself.
I can say from our point of view, productive machines, we've seen a huge variation as well. So it depends, like you say, very much on how much optimization has been done beforehand. So on occasions we have done more than 100% improvement, but something that's been extremely optimized, maybe 5%. So it really varies of the processes and what's been done beforehand in terms of optimization. Got another question here. On a CNC machine with a flattened mill, what's the best location for placing the sensors and do a tap test? At the lower point of the tool or the spindle?
At the lower point of the tool, where it's the most flexible. So if you do it on the spindle is way rigid than that of your tool tip. So you want it at the tool tip.
So someone's asking here, we are tap testing small tools, less than 6 millimeters, and we have got a very noisy response. It is very complicated to analyze. Is there a way to improve the signal to noise ratio?
One of the things I'll say is when you're having a lot of noisy feedbacks, check your cables. Are your cables, the accelerometer cable can be very, what's the word I can use? Can be flimsy sometimes, especially those blue wires. So check them that they're well tied up. Check your armors, that everything. If everything is fine, then another way you can use to make it better is do a model analysis on it, which it depends on what software you have, and that way you can do a curve fitting on it and extract it and get rid of the noise. Anyone else that want to help me out here?
Yep, agreed. Your answers are very accurate piece. So
yeah.
Okay. So we have one more question here. How would one apply SLD on a face miller with a, for example, 45-degree entrance angle? Is this applicable or is it subtesting only useful for end mills?
So the stability loop diagram they're referring to there, the software, you can specify what your cutting tool looks like. You can specify the geometry as well in the software that we've got. So I haven't personally done a stability loop diagram with that type of cutting tool, but I think there is an option to put that into the software.
Okay, thank you very much. Okay, if we haven't got any more questions, then I will bring this to a close. We can get in touch with us, please, if we have intrigued you or inspired your interest in tap testing, please do get in touch with us at productivemachines.co.uk. Thank you very much to the panelists And thank you very much to the audience for joining us today. Thank you.
Thank you
And
very
goodbye.
much.
Yeah.
Everyone.
Thank you very much.